Okay, I just want to bring the book. So last time we looked at, let me put the screen. We looked at e to the x. So the function e to the x, that was an easy one to do, and it's just x to the k over k factorial. All the derivatives were easy to put, and we could figure this one out, and the interval of convergence was everything. So from negative infinity to infinity. This is one important power series, one that you should know. It will be useful in general. So it's good that you know it in general. And I'm already writing e to the x equals here, but that's part of what we, so right now let me write it like this. So let me write instead power series of, or Taylor series of e to the x is this one. And it actually equals e to the x, and that's some of what we're gonna be learning today. So why is it that it equals e to the x? So, but before that, there's another one we need to study, which is the binomial power series. So I want to talk about this one now, binomial power series. So what is a binomial power series? Well, for those of you that have taken a little bit of counting, you may remember these numbers over here. These numbers, let me write them like this: n choose m, right? They're called binomial coefficients, and they're defined as n factorial divided by n factorial by n minus m factorial. Or, this is probably the better one to write here, n times n minus 1 times n minus 2 times n minus m plus 1 divided by m factorial. Now, these binomial coefficients come because of the binomial theorem, right? Do you remember whenever you want to write something like this, you know, a binomial x plus y, and you want to raise it to a power, say to the power 2, we know that this is x squared plus 2xy plus y squared, right? If you want to do a larger power, let me do 3. And so 3 is this one. So not too big, but okay, now let me go considerably bigger. Let's go x plus y to the 6th power, right? If you've ever wondered how you can do x plus y to the 6th, well, this is this one over here. And I'll tell you in a moment where these numbers come from. See, this is, next one is 20, I believe. 15 x squared y to the 4th, 6 x y to the 5th, and last y to the 6th. Right, lots of terms, right? And the terms are not that difficult because this is to the 6th, then to the 5th, to the 4th, to the 3rd, to the 2nd, to the 1st. Oh yeah, to the 1st, and no x's. And the y's the other way around. No y's to the 1st, to the 2nd, to the 3rd, to the 4th, to the 5th, to the 6th. All right, this is nothing that has to do with calculus. I'm just want to motivate where these binomial numbers, binomial coefficients come from. All right, this over here, this is called the binomial coefficient. Binomial coefficient. And those are these numbers over here. So this number 6 is 6 choose 1. This 15 is 6 choose 2. This 20 is 6 choose 3, or the binomial coefficient 6, 3. This is 6, 4. And this is 6, 5. And well, this one over here is 6, 6. So it's the number 1. And this one is 6, 0. That's where these numbers come, right? And let me show one of these to you. For example, let's do 6 choose 2 using this formula over here. So 6 choose 2, according to this formula over here, should be 6 times, let's see, it's going to be times 5 times 4 times, let's see, okay, let's 6 times 6 minus 1 times 6 minus 2 all the way to 6 minus 2 plus 1 to 6 times 3 divided by, oh, I made a mistake here. That's why it's throwing me off. This should be m factorial. Sorry for that. So now is this correct? Let me check. Oh, okay. Yeah. So again, I'm supposed to go 6 minus 1, 6 minus 2, all the way to 6 minus, and my number is 2, 6 minus 2, 4, plus 1, 5. So it's only 6 and 5, divided by 2 factorial. So this is 30 divided by 2, and that's 15. So that's how I know this guy is 15, right? We can do 6 choose 3 as well. So let's do 6 choose 3. 6 choose 3 is going to be 6 times 5 times 4 divided by 3 factorial. And this is 6 times 5 times 4 divided by 6. The 6's go away, so that's 20. And that's how I know this guy is 20. All right? So these are the binomial numbers, the binomial coefficients. And they are helpful when you want to take some number and raise it to a power, right? Like in this case, binomial, and I wanted to raise it to the 6th power, or to the 7th, or to the 8th, or to the 10th, right? Now, if I do it to the 10th, the only problem is that I get more terms here, right? This keeps going on. Now, here's the nice thing. The nice thing is that we can also use this to raise one of these numbers to an arbitrary power, like to the power 1/2 or to the power 3/2. The only thing we need to do is we need to we need to do it with a series, right? Harnit is asking me that can we also find these numbers using Pascal's triangle? And you're right about that. So that's how they relate to combinatorics, right? So if you put these numbers in an array like this, so 0 choose 0, 1 choose 0, and 1 choose 1. Then 2 choose 0, 2 choose 1, 2 choose 2. And then 3 choose 2, and 3 choose 3. And then 4 choose 0, 4 choose 1. This is called Pascal's triangle. And the idea is that then you can find out what these numbers are by simply doing the following. Figuring out that all of these that are choose 0, if it's choose 0, they're all ones. And if it's some number choose itself, those are also ones. So the ones in the outside are all ones. So the entire thing starts like this. And then if you want to find out the one that is here, you just take these two and add them. 1 plus 1, that's 2. So then it's like this. 2 plus 1, 3. 1. 1 plus 3, 4. 3 plus 3, 6. 4, 1. And then 5, 10, 10, 5, 1. And okay, these two now are so this tells you that this number 4 or this number 6 is the same as 4 choose 2, right? That's how you can figure them out. Let's go one more line so you can see the ones that I had created over here. If we go one more line, it would be 1, 6, 15, 20, right? These are precisely these numbers. 1, 6, 15, 20. All right? Is that clear? All right. Now, if you're getting scared about all of these, don't be, because this is, I'm just trying to put it in context. There's no calculus here. This is material that maybe you knew from before, maybe you didn't, and you're learning it from the first time. That's fine. Here is the calculus part. So the calculus part is if we want to come up with a power series for the function 1 plus x to the p. So that's our goal, right? So this is example. So for the binomial series, we want to find a Taylor series or a Maclaurin series for the function 1 plus x to the power p. So we're simplifying it a little bit. Instead of doing x plus y, because then you get two variables, we're only going to do it for one variable here. So 1 plus x to the power p. So that's our function, 1 plus x to the power p. And now we need to come up with the Maclaurin series, right? So how are we going to do it? Well, we're going to do it with our definition, right? So here is what it is. The Maclaurin series is the series from 0 to infinity, the kth derivative at 0 divided by k factorial x to the k. And all we need to do is find out the derivatives, the kth derivatives, and plug 0, right? So as usual, let's do a little table here. So here's k, and over here we're gonna do the kth derivative at x, and over here we're gonna plug 0. All right, let's do it. So starting with 0, the original function is just 1 plus x to the p, and when we plug 0 we get 1. So far so good, no problem. First derivative, well, here's the thing, the p comes down, and then is 1 plus x, and you subtract 1 to the exponent, correct? And what happens when you plug 0? You get p, right? Now, this p, by the way, I'm going to write it as you'll see in a moment why. This p is the same as p choose 1. Let me write the definition over here on the right of what p choose k is. To remind you, I mean, so here's the definition. P choose k is p minus 1, p minus 2, p minus k plus 1 over k factorial. So my bad, this is actually, I mean, yeah, this is p choose 1, but I don't want it just yet. Let's wait for that, my bad. Let's continue. So second derivative. So here's what's gonna happen. For the second derivative, this p minus 1 is gonna come and multiply the p, right? So now it's p times p minus 1, 1 plus x to the power p minus 2. And what happens when we plug 0? 0 for x makes this number 1. So all that's gonna survive is the p and the p minus 1. So we're gonna get p times p minus 1. Correct? Do we see a pattern now? Let's keep going. Let's do one more, maybe two more. So next derivative, the p minus 2 comes down and multiplies these guys. So it's p minus 1, p minus 2, and then times 1 plus x to the p minus 3 times the derivative of 1 plus x, which is 1, right? So no problem. And then when we plug 0, we get p minus 1, p minus 2, right? Do we get a pattern now? What is the pattern? What's going to be the next one when we plug 0? This is really what we need. So at every derivative, the only thing that's happening is we're taking these numbers and bringing them down, right? And subtracting 1 to the exponent. So the next one will be p minus 1, p minus 2 times p minus 3. Correct? Are we ready to write down? Yes, thank you, Harnit and Miguel. Very good. So if we continue all the way to the kth one, right? Let's see if we can write it in general. So what would be the kth one? Well, let's see. What's the pattern? Let's look. If when we go to 3, we go p minus 1, p minus 2. We stop one less. When we go to 4, we go p minus 1, p minus 2, p minus 3. We stop at 3. So we stop at one less, right? So for k, it's going to be p minus 1, p minus 2, all the way to p minus 1 less than k. And then 1 minus 1 plus x times p minus to the power p minus k. And then when we plug 0, it's going to be p minus 1, p minus 2, dot, 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 all the way to p minus, and we stop at one less. P minus k, parentheses, k minus 1. Is that clear? Yes? All right. So we got it. We got the pattern. And now let's just put all the ingredients together, right? Let me go back a little bit and show you what we need to do. So we discover what this number is. So we just need to plug it in here and divide by k factorial, right? So let's put it over here. So the Maclaurin series for 1 plus x to the power p is this number we discover, which is all of these, the multiplication of a lot of things, divided by k factorial, x to the k. All right? And we're done with finding out the Maclaurin series for this function. But the important thing is now, I mean, remember this number over here and compare it to the binomial coefficient that we put over here. Here's the formula for the binomial coefficient. And you'll be like, hey, professor, they're the same. They're exactly the same. This number in purple and this number that we discovered, they are exactly the same. So we can write it in a shorter way as follows. We can write it as p choose k, x to the k. This is how you read this, by the way. So let me write it because that's important. So to write, you can, this number over here is the binomial coefficient pk, and you read it as p choose k. And if you're wondering why, it's because it has a combinatorial meaning. See, if you have, say, 5 shirts, and you wanna, or you have a group of 5 friends, let's put it that way, 5 friends, and you wanna choose 2 of them to make a committee, to do a group. They're gonna be the leaders of the group. In how many ways can you choose 2 out of the 5? And the answer is 5 choose 2. The binomial coefficient 5 choose 2, which is 10, by the way. 5 choose 2 is equal to 10 if you plug the numbers and figure it out, right? So this is why we read it p choose k. All right, so if this is giving you trouble, don't worry. Then just remember that this number p choose k is just an abbreviation of all of these, because this looks kind of complicated. Instead of writing all of these, we write this symbol, p choose k. It's an abbreviation of that, all right? So this is an important series. It's called the binomial series, right? So this one over here, it's called the binomial series. All right, and same as always, whenever we get a new series, a new power series, a new Taylor series, a new Maclaurin series, the first question we ask ourselves is, where is this series convergent, right? Let's find out the radius of convergence at least. The interval is a little bit tricky for this one. It depends on the p. So this number p can be whatever we want. It can be an integer. It can be a rational number, like 1/2. It could be a number like pi, and that's okay. So let's find out what is the radius of convergence. So what is the radius of convergence? Okay, and how do we do it? What is our technique? Anyone? Ratio test, absolutely. So the ratio test is our usual way. So we need to do the limit when k goes to infinity, ak plus 1 divided by ak in absolute value. And let's write it down. What is ak plus 1? Okay, maybe I shouldn't erase it. Here's the k term, right? So it's going to be p choose k plus 1, x to the k plus 1 times, and then the other we just flip it, right? So it will be 1 over p choose k, x to the k. All right. Now I can move it up. Good. Now let's figure out this limit. First, as usual, this x to the k goes with the k, so only the x is going to survive. So we get the limit when k goes to infinity of p choose k plus 1 over p choose k, absolute value of x. Maybe I don't know if these are positive or negative, so let me leave the absolute value bars over these other guys, the binomial coefficients as well. All right, now we need to do the limit, so we better simplify this expression a little bit. So we're gonna go back to what these mean, right? And let me write it right here in the corner, a reminder of what these coefficients are. So p choose k is equal to p minus 1, p minus 2, continue all the way to p minus parentheses k minus 1 over k factorial. All right, so let's do it here. So it's the x that I'm gonna put first because we don't care too much about it. And then we have this is p minus 1, p minus 2, dot, 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 all the way to p minus parentheses k minus 1. But now I have k plus 1, so I'm gonna stop at p minus k over k plus 1 factorial. And all of that over p minus 1, p minus 2, p minus parentheses k minus 1 over k factorial. Right? Okay, that's good because a lot of things cancel. These p minus 1, p minus 2, all of these terms cancel with all of these, all the way to the previous one before. So the one that comes right before this one would be, so the right behind this one is p minus parentheses k minus 1, right? So I should cancel that one with this. So only p minus k survives. And I should have done the same with the factorials. In fact, let's do it. What is k plus 1 factorial? K plus 1 factorial is 1 times 2 times 3 times 4 all the way to k plus 1. And k factorial is 1 times 2 times 3 times 4 all the way to k. So these also cancel. Only k plus 1 survives, right? So this becomes the limit when k goes to infinity, absolute value of x divided by p minus k over k plus 1. All right. Now, what is this limit, right? We simplified it as much as we can. So now k goes to infinity, right? And now what happens to this limit? Well, don't worry about the p. The p is a constant. It's just some number that we don't know about. So then the variable here is k. And you know how to do this, right? We look at they're both polynomials. So we look at the largest degree. The degree on the top is 1. The degree on the bottom is 1. So they're both degree 1. So then we look at the coefficients. And what's the coefficient of this one? -1. What's the coefficient of that one is 1. So this limit will be -1, but it's inside the absolute value, right? So all in all, this is going to be absolute value of -1, which is 1. So this is just x. All right? Yeah, not x times p, Daniel, just x, right? So it's p minus k. The coefficient is not the p, it is coefficient -1. I'll explain it a different way. Here's a different way of explaining this limit. You can divide everything by k. So it's going to be p over k minus 1 divided by 1 plus 1 over k. And now these guys go to 0, right? Because you're dividing by something big. So you get absolute value of x times absolute value of -1, which is absolute value of x. Right? A different way of explaining it, but it's all the same. And then let's not forget what we were doing. We want to know if this is less than 1, it's going to be convergent. Greater than 1 will be divergent. So x than 1, less than 1, convergent. So that tells us that the radius of convergence is 1. All right? And that's all we want to know. Because the interval of convergence to check the endpoints is difficult. It depends on the p. It's going to be different when p is an integer or when p is not an integer. So let's not worry about that. Let's just say that this new Taylor series that we came up with, so the Taylor series, Maclaurin series, because it's centered at 0. The Maclaurin series for 1 plus x to the p is p choose k, x to the k from 0 to infinity. And it converges for -1 less than x less than 1. The endpoints may or may not be convergent depending on p, right? And we're not gonna do that, but this is as far as we want to take it. Instead, what I want to do is do an example, and then we'll move on to the other question, the question about when is it that the Taylor series or the Maclaurin series equals the function. All right, so let's take a look at example 5. Let me see if I can put it in the book. And we want to take a look at example 5. All right, example 5, right there. It says, consider the function f of x equals the square root of 1 plus x. Find the first 4 terms of the binomial series for f centered at 0, and then approximate the square root of 1.15 to 3 decimal places. Assume the series for f converges to f on its interval of convergence, which is -1 to 1, right? So indeed, here they're telling us a bit more of the information that that we had, which is fine. All right, so let's see if we can do it. So our function is square root of 1 plus x, which we can rewrite as 1 plus x to the power 1/2. I'll move to the page in just a moment. Okay, so here's our function. And we want to write down the power series. So it's Maclaurin series. So we learned that 1 plus x to the p is this one, p choose k from 0 to infinity x to the p. And this is good between -1 and 1. In fact, for this particular p, with p equals 1/2, it's okay to use -1 and 1. That's what the book says. All right. So then let's in our case, p is 1/2. So we're doing 1 plus x to the power half. So that would be 1/2, choose k, x, that's a mistake here, this should be k, x to the k. And fortunately, they're not asking us to get all of them. It says only get the first 4 terms, right? So we only need to figure out what is 1/2, choose 0, 1/2, choose 1, 1/2, choose 2, and 1/2, choose 3. Those are the only ones we need, right? So let's see if we can get them. Remember what the formula is, right? Maybe I should, again, bring it over here. So I'll write what p choose k is in purple here. Is p minus 1, p minus 2, all the way to p minus 1 less, k minus 1, divided by k factorial. So, oh, and anything choose 0 is 1. That's a special case. It doesn't make sense to do p minus -1. So p choose 0 by definition is 1. So this one is 1, nothing to do. 1/2 choose 1 will be 1/2, and that's it, because k is 1. So you use 1 minus 1 is 0. So you only have one term in the product. 1/2 divided by 1 factorial. So that's just 1/2, right? 1/2 choose 2. Well, that's going to be 1/2 times 1/2 minus 1. Remember, you do 1 less. So you do, if this is 2, you stop when it's 1/2 minus 1. Divided by 2 factorial. So that's 1/2 times -1/2 divided by 2. So this is -1/4 divided by 2. That's -1/8. And last, 1/2 choose 3. That will be 1/2 times 1/2 minus 1 times 1/2 minus 2 divided by 3 factorial. So that's 1/2 times -1/2 times 1/2 minus 2. That's 4 halves. So that's -3 halves divided by 6. So that's negative times negative, that's positive. So in the top is 3/8 and in the bottom is 6. So this is 3 over 48, 3 over 6 times 8. So that's 1 over 16, I believe. If I did everything right. Okay. So that's it. So how does the power series starts? So it starts like this: 1 plus x to the 1/2 starts like 1 plus 1/2 to the x minus 1/8 to the x squared plus 1/16 to the x cubed, and then more stuff that we don't know because we only did the first 4, right? We only did the first 4. We don't know the other ones. But that's all we were asked to do, so we're good. Okay, so we're completed part A. Now part B says approximate. So part B says approximate the square root of 1.15 to 3 decimal places. So how do we relate square root of 1.15 to this function, right? In other words, what should I plug? What x should I plug here so that I get square root of 1.15? Yes, 0.15. Thank you, Michael and Gerardo. Right? So then we just put it in here. and our approximation will be 1 plus 0.15 to the power 1/2 will be approximated. It's going to be an approximation because we're not going to use all of them, right? We're only going to use these first 4. So it's going to be 1 plus 1/2 of 0.15 minus 1/8 of 0.15 squared plus 1/16 of 0.15 to the cube, right? And if you're patient, you could, in theory, do all of these operations by hand. So the book says that this is about 1.072, which matches nicely. It approximates the square root that we wanted with 3 decimal places in the right way. Okay? All right. Questions? All right. So now to the big problem here with Taylor series and Maclaurin series, which is, I mean, I'm already using it here. I don't know if you realize. See, I wrote equal right here, right? I wrote that this is equal to that, but we haven't checked that. And this is the Taylor series, and we don't know if the Taylor series actually equals the original function, right? Good news is that that will be the case for most of our functions. So for most of the functions that we know, you know, like sine, cosine, e to the x, this one, the binomial, or arctangent, or ln, for any of those, it will be the case that the Taylor series will be equal to the original function. Okay? Now, how do we justify that? Well, the way we need to do it is to go back to our old Taylor polynomials, right? When we started chapter 11, before any of this madness, right? When we were still at school, we learned about polynomials, right? The Taylor polynomials. Let me write it here. Taylor polynomial Pn, that was the k derivative at a divided by k factorial x minus a to the k from 0 to n. And you may remember that we talked about the remainder. Can I repeat what I just said? Yes. So we're gonna try to see. So the question here is when is it true that the Taylor series equals the function?
Professor?
Yes.
One of the students said, please, can you repeat what you just said? They weren't able to hear you because they lagged out.
Yeah. Thank you. I think I was saying that. So this is a question we're gonna look at now. When is it that the Taylor series equals a function? In fact, let me take you back to the book. Let's take a look at the book. See, when we started this section, this was page 731. Give it a little bit of time. All right, right here, 731. When we learn about Maclaurin series, we had these 2 important questions. First, it says, for the Taylor series to be useful, we need to know 2 things. First, the values for which the series converges. That we can know, right? That part we have been doing quite well. We just find the radius of convergence, and we can even test the endpoints often. And then here's the second part, the values for which the Taylor series equals the function. That's what we want to know, right? That's going to be awesome. And it says the second question is subtle, and it will be postponed for a few pages. And so that's the part that we're doing right now, the subtle part. Okay? So, and I'm telling you how we're going to do it. So the important thing is to remember the Taylor polynomials. When we saw Taylor polynomials at the very end, we knew that we also had something called the remainder. So if we have the function is equal to the polynomial plus the remainder It's kind of like the error, right? Because we know this guy approximates the function. Remember when we saw several pictures, how the larger the polynomial, the better the approximation was. It became better and better and better. And then we had the remainder. This is called the remainder. So recall that the remainder, R of n, satisfies this bound. It's equal to the n plus 1 derivative at some number c, x minus a to the n plus 1 divided by n plus 1 factorial, for some c between x and a, right? We did this before. So this was back in 11.1. And you even have a homework where you're asked to find the, the error, bound the error using this. And the idea is always to find a bound for this term, for the derivative, the n plus 1 derivative, right? And you may remember that I told you that this formula is not that complicated. It's like the next term here. So if you go n plus 1, with the difference that you plug a special number c, which is between x and a, right? So then using this, we can answer the question, when is it that the Taylor series will be equal to the function? Well, the Taylor series is when you take n go to infinity, right? So answer to this question, the answer to that question is f of x will be equal to the limit of Pn of x, and the limit is precisely what we want, is when we go to infinity here. That's the Taylor series. If the remainder goes to 0, right? Let's go back here. So this becomes the series. So if we want the series to be equal to the function, then this part has to be 0. This part has to go to 0, all right? So that's what we need to argue. So that's the answer. The Taylor series equals the function when the remainder goes to 0, when the limit of the remainder goes to 0. So now, what we want to do is see if we can show that, at least for a few examples. So that's what we're going to be doing now. So let's do example 7. So this is page 738. Let me put it on the book. All right, so this is what we want to show. We want to show that the Maclaurin series for e to the x is equal to e to the x when we are between negative infinity and infinity. So all over the place, all right? So that's what we want to show. Example 7. And we already know what is the Maclaurin series for e to the x. Is x to the k over k factorial, the one that you see right there. Okay, so let me switch back to the paper. Okay, so why is it, how do we argue that this is actually equal to e to the x? Why is that? Well, all we need to do is show that the remainder goes to 0, all right? So what is the remainder for the function e to the x? And here's the formula for the remainder, right? It's right here. Here's the formula for the remainder. So let's write it down. What would be the remainder? So for f of x equals e to the x, the remainder equals Rn of x is the n plus 1 derivative at c times x minus a to the power n plus 1 divided by n plus 1 factorial, right? But what is the f? Well, the function in this example is e to the x, right? So what is the derivative of e to the x n plus 1 times? Anyone?
Can you repeat the question?
Yes. So the question is, what would be the derivative, the n plus 1 derivative of e to the x? Yeah, it's e to the x, right? All the derivatives are e to the x. So then I plug c. So this will be e to the c. So it will be e to the c times x to the power n plus 1 over n plus 1 factorial, right? Now, and what do I know about c? Well, c is a number between 0 and x. Right? So all I need to do now is to argue why this goes to 0, right? For an arbitrary x. So first, what is the most that this number e to the c can be? So e to the c is an increasing function, right? So let me do a little picture here. Here's e to the x. And we are between 0 and x. So c is somewhere in between, right? So what is the most that e to the c can be? Well, c is between 0 and x. So the most that it can be is when I pick x, right? When I go all the way over here. Well, that assuming that x is positive. If x is negative, then the most that it can be is 0, right? But in the worst case scenario, is at most e to the x. So note that e to the c is less than e to the x if x is positive, right? If my picture is like this. If x is negative, then it's less than e to the 0. E to the 0 if x is less than or equal to 0. All right? Because remember, I want to bound this. So that's what I wanted to do. I want to do the limit of this quantity. So let me go to the next page. We want to bound. We want to bound the absolute value of Rn, right? We want to make it small. And what is that? Well, that's the absolute value of e to the c, x to the power n plus 1 over n plus 1 factorial. And we already said that e to the c is at most e to the x. So if x is positive. So this is the less than e to the x to the n plus 1 over n plus 1 factorial. Right? Okay. Now, what I want to show is that this goes to 0. All right? And I'm going to show it indirectly. So we want to show right-hand side goes to 0 when n goes to infinity. If we pick really, really big numbers. And why is that? Well, see, remember, we want to do the limit when n goes to infinity. So forget about the x, right? This part we don't care about. It's just a constant. The e to the x is scary, but x is not moving. So this is just a constant. The thing that is moving is n. So I want to show that this goes to 0. And why is that? I'm going to do it indirectly, right? Let's remember this. So let's go back and let's do let's pause here and go back to this. this series, x to the n over n factorial, right? That's the Taylor series for e to the x, right? And last time, yesterday, we showed that this is converges for any x, right? We saw that the radius of convergence for this one was infinity. Convergence for any x. Notice that I'm using n instead of k. That's on purpose. I'm not doing it just to throw you off. I changed this letter n for a reason. Here's the reason. I want to use now the divergence test. What's a divergence test? The divergence test tells you that if this limit, if this series converges, then the limit of this term is what? So the divergence test, you usually do it the other way around. If the limit is not zero, then it diverges, right? But really what happens is that if it converges, then the limit of these terms has to be zero, right? So by divergence test, the limit when n goes to infinity of x to the n over n factorial is zero, right? And that's the same as if you change the x to n plus 1. It doesn't matter, right? It's just like doing a j substitution. In this case, an n substitution. So this limit is also 0, right? So then we can look up here, and then this part over here goes to 0 when n goes to infinity. And because this part goes to 0, then the remainder goes to 0. So this one, it's less than or equal this one, which is e to the x times x to the n plus 1 over n plus 1 factorial. And this one is just a constant. We can take it out. So this is 0, right? So this is a limit that is less than 0, but it's also greater than or equal 0 because it's positive things. So because it's between 0 and 0, it is 0. The remainder goes to 0. And that's great, because if the remainder is 0, then that means the function is equal to its Taylor series. So now we can write this with confidence for any x. All right. Questions? All right. We still have. I want to do another one, but so we're gonna check that it also happens for cosine x. Now, if you think this is difficult, you are right. So generally showing that the remainder goes to 0 is difficult. So we're gonna do a couple of them. So we did e to the x. We're gonna do next week. We're gonna do cosine x. But mostly we're gonna assume that happens in general. So we're going to not worry about that. So the important thing for you to know now is, I want to show you a page from the book that I think is important that you start familiarizing with that page yourselves. So on page 740 on our book, there's a table of our important Taylor or Maclaurin series that we worked on. And this is like a library of important series that you should know. So let me see. So take a look at this table 11.5, because it has all the important ones that we saw. So it starts with the geometric series, which was our go-to guide to get all the other ones. Then we have 1 over 1 plus x. We have e to the x. We have sine, cosine. ln, negative ln of 1 minus x, inverse tangent, which we figured out the other day. These ones, don't pay attention to them. You can skip those, the hyperbolic sine and hyperbolic cosine. And then at the end, the binomial one, which is the one that we worked on today. All right? So start looking at this table, study it. You should pretty much know all of these by heart, right? They're all important ones. So it's very, very important that you know them. All right? And is there anything else? Any questions? All right. If not, I'll see you guys next week. Remember that I'm posting all of our video sessions. If there was, I know that there's always some lag at around noon. I think the cable company somehow is slowing down the internet on purpose, or maybe it's because at that time it's when the most of us are connecting. So don't worry if there were some parts that you didn't listen to. You can always go back and listen and look at the videos that I'm posting. You can find them directly on YouTube, or you can follow the links that I'm posting on our Canvas page. All right? Any questions? Okay, guys. Have a great weekend. See you next week.